Hello, everyone. Let's discuss about abstraction of storage devices at operating system level, such as files and directories. Before we jump into the detailed discussion about the concepts of files and directories, can you think why do we need to learn about these concepts? Well, maybe you are thinking because you need to score good on the test, you need to get a good grade in the course that includes these concepts. Maybe you need these concepts for a project that you're working on. And many others. But still not quite convincing, not quite motivating to spend all the time and efforts. Let's think in a different way. Can you imagine a day in your life without accessing any file or directory? Well, many of you might be thinking, yeah, obviously, all files are stored on this big rack. That room is very dusty and nobody goes to that room. Or maybe even many organizations doesn't even have anymore that room. It's not those files that we are talking about. We are talking about the files stored on computer systems. So rephrasing the concern here. Now, whenever you open any mobile devices, like phone, whenever I open my phone, I'm accessing files and directories that are stored on my phone. Whenever I go to any web address, I'm accessing some files and directories on a remote server. Whenever I open my laptop or my workstation, as soon as it boots on, during the process of booting on itself, I'm accessing files and directories. So now imagine a day without doing any of this. And how many days like this you can stay? Well, maybe if I'm roaming in national forest where I don't have any internet or mobile coverage, cell phone tower, then a day or two, a long weekend. But eventually we would need to access files and directories. And mostly we access many files and directories right from the time when we wake up in the morning until we sleep almost every day. So this shows the importance of files and directories into the life that we are living today. And this makes it interesting to learn more about it, because if it's something that's this important part of our life, we should know about it, right? Okay, so as I mentioned in the beginning, files and directories are operating system level abstractions of storage devices, such as hard disk, SSDs. What other abstractions can you think of? So we have process as abstraction of CPU in our computer systems. We have address space as abstraction of memory, such as main memory, DRAM, RAM, in our computer systems. But what we are going to talk about in this lecture is files and directories. These both constitutes the abstractions of persistent storage. Persistent storage can be hard disk, SSD. So basically we store the data that matters to us the most, and we don't want this data to be lost every time we switch off a device, or every time some components from the device are disconnected, or any other eventual situations of closing the program, opening another program, shutting down the device, anything like this. So we don't want the data to be lost by any such instances. We want this data to stay permanently, almost, maybe permanent is a very long term, right? So maybe very long lived data, let's call that. So if we think that the piece of data is important to us, we want it to be long lived, then we store it on a persistent storage, such as hard disk or SSDs. And operating system level abstraction of this data is in form of files and directories managed by file system. So before we jump into the concepts of learning about different file systems, first, definitely we need to learn about what are files and directories, what are different interface through which we interact with files and directories, and how do we perform different operations on files and directories, how these abstractions are managed. So file is linear array of bytes, each of which we can read and write. Now, in the operating system, each file has a unique name. That's the language in which operating system would understand. We could call in, normally in many storage systems language, this unique name that operating system calls for each file that we have on the system, this low level name for each file is called inode or inode number. We would be using inode number terms in this lecture. So you know that what do we mean when we call something like inode number. So here inode is a data structure, and each entry in inode table is uniquely identified by inode number. So each file has its own inode structure, and each file thus has this unique inode number by which operating system recognizes this file. So with this basic terminologies now clear in our head, let's learn about how should the OS manage a persistent storage. Any ideas, any thoughts? So many thoughts, right? Managing something is not an easy task, and managing all the data that matters to anybody is definitely not an easy task. So let's learn about that how does OS does this management. So first, let's take a simple example of how these files and directories are represented. And when we refer to things like directory hierarchy, what underneath at the system level, what does it mean? So for example, let's take a file. You can name your file as your name, or let's call it a foo. And this file foo has inode number, which is unique to each file. So inode number 10, then this inode number 10 cannot be used for any other file. Now, the directory that stores file foo or contains file foo will have information or will store information such as the file name, which is foo.txt, and its inode number, which is unique to this file. So directory, any directory in the system would usually store information such as file, inode number, or a directory can have a directory inside it, right? Such as you can create a folder ABC, you can create a folder D inside it, folder E inside it, then inside folder D, you can create folder Z, something like that. So a directory can either have a file inside it, or a directory can have another directory inside it. So in that case, this directory can also store another directory and its inode. So such a structure where there is a directory, that directory can have other directories inside it or files inside it. Now these other directories can again have some other files inside it or some another directories inside it. Such a structure could be represented as hierarchy. We can call that as directory hierarchy. Or directory tree. And under this directory hierarchy, all files and directories are stored. Always a directory hierarchy would start with a root directory. We call it in the Unix systems, we call it root. In most of the operating system, that's called root, which is the starting point of this directory hierarchy. In Unix systems, we represent root as this /. So a sample of directory hierarchy could be something like, let's say this is our root. Now inside root, we have directory called bar. We have a directory called A. Inside bar, we have a directory, or let's say we have a file called foo.txt. Inside directory A, we can have another directory C, another directory B. Now inside directory C, we can have another directory B. We can have a file foo.txt over here. Inside B, we can have directory bar, and we can have another file z.txt over here, and so on and so forth. So if you see this directory hierarchy, and if you are observing it closely, apart from my drawing skills of drawing it very well, if you're observing the content inside this very spectacular drawing that I made, then you would see that foo.txt could be the same file with the same name, but stored under different directory. Now, if there are two files that have same name, that doesn't ensure, or that doesn't guarantee that the content inside those files are the same. It could be same, it may be different, something, but doesn't matter. If there are two files, each of this file will have its own inode. So let's say this file is represented by an inode that has inode number 10, but this file will be represented with another inode that would have a different inode number, let's say 12. And another observation you would have made is we have two directories with the same name. Still, it doesn't matter, because if we want to refer to this directory, then the path to that directory is root bar. But if you want to refer to this directory, then the path to that directory is root, directory A, directory B, then directory bar. So each of this is unique on its own. So it doesn't matter if they have the same name. And eventually, for an abstraction of files and directories for operating system, it literally does not matter what is the extension of that file. Rather, it could be .txt, .png, .c, whatever you want. So basically, you can have a .c file and you can decide not to write a C program inside that .c file. It wouldn't matter to operating system. But why these extensions are useful is it gives our devices a hint of what application to open this file with. So it binds the backend with front-end applications. And that's the level at which we use this extension. But for an operating system, just to manage the data that it's storing, it doesn't need to make sense of these extensions. For a operating system, it's just something, one file represented with a unique inode number. All it matters is the inode that it stores related to this file. So do you think if we have a system in our house, let's say it's a very, very smart AI, anytime we need anything, let's say I want to wear a red dress for Christmas, then I just ask that system, hey, fetch me a red dress with black polka dots that has full sleeves and which is full length, something like this. That system exactly knows where this dress is and fetches me that dress, gives me that dress right in front of me. I don't have to take any efforts of going and searching that in my wardrobe, or maybe I have this very big house which has multiple rooms and each room has multiple wardrobes. So then imagine the search complexity. Or maybe this dress may not be in any wardrobe. It might be stored in an attic, in a suitcase, in a bag, something like that, right? Oh my God, that would take so much time. Now, anytime I buy something new, I give it to the system and the system magically knows where to find, it knows where to find space for that, and it stores that in that space. Now, how challenging would it be to design such a system for your house, which can fetch you whatever thing you want, and if you get any new thing, then it knows exactly where to store it. Such a system for a computer system is the file system, because if we generate any new data, we give it to the file system, it knows how exactly to store on the storage devices that are available to that system. And whenever we want any data, irrespective of that complexity of looking exactly inside different address space of different storage devices that we have on that system, we just ask the file system that, hey, I want this data, open this file. And it just knows exactly from where to fetch that file, where it was stored, what offset are you requesting to give to you in that format, so that then you can either read, either update, or do any operation, basically access the data that's in that file. And then finally, sometimes if when we don't need any data or if we think this data is no longer required, we just say to file system, hey, delete this data for me. And then it takes care of removing that data from the persistent storage device. So managing all these operations is definitely a challenging task. And mainly what we need to do, the different interface that we require for managing these operations efficiently are, those can be called as file system interface, consist of three main operations. First, creating. Second, accessing. Third, deleting. So creating, that includes opening files, making directories, right? Accessing. Now, when we want to access any data, what is it that we usually do with that? Either we read it or we write or update it. So read or write files. Now, these read or writes could happen in a sequential fashion or a random fashion. Maybe I want to read an entire file, or maybe I want to read just a variable stored at a particular location in that file. What else do we do when we access content on operating system? We operate with directories. So we read directories. In order to parse the directory tree, we would have to read directories. And finally, for any data that's no longer required, we want to delete files or any directory that's no longer required. We would want to delete directory as well. And file systems interact with a simplified interface of devices. We call this as block interface or a block layer. And just having a block layer simplifies the management for a storage device.